Good morning, students. Welcome to the class on NMR spectroscopy. We were discussing second order spectra as part of advanced topics. Now we will look at AB2, AX2 type systems. What is AB2 or AX2? That means we have one proton and a carbon, and we have two protons and another carbon. Say then it is A and it is B type, or if it is X type we call it as AX2, if it is B type we call it as AB2, right? Now we will look at the spectra with respect to changes in the values of delta nu by J. When we have a delta nu by J value of 10, then the spectra is very clear. It is a first order spectra, and we call it as AX2 because it is a first order spectra. That means A proton will give a triplet because it is having two alpha protons. B protons will give a doublet because it is having one alpha proton. So in this case, we can clearly see this doublet and triplet. So this is for A type protons and this is for X type protons. The delta value will be the middle of the peak. How do we measure the delta? Delta will be middle of the peak. In this case, it is middle of the peak. Right. When we decrease the value, of delta nu by J to 5, then what will happen? It becomes little bit complex. The multiplet becomes little bit complex. We cannot expect the multiplicity based on n plus 1 rule. It is a complex system which needs theoretical mathematical calculations to explain the splitting. So that means in this case, the transition between first order and second order, it is occurring somewhere between delta nu by J value of 5 and 10. So the transition is occurring here. When we have delta nu by J value of 10, it is very clear, it is a first order spectrum. But when we have delta nu by J value of 5, it becomes complex. When the value is 3, the complexity will further increase. That means the delta difference between these two peaks will further decrease. The complexity will further increase. If we have a value of around 1.5 or 1.0, then it becomes a single multiplet. Here we can see this multiplet and this multiplet with some small separation. But when we have delta nu by J value of around 1 or 1.5, then this multiplet, it becomes very complex and we don't see two different multiplets. We see only one multiplet. So in this case, what we can say, it has become perfect second order and it is now AB2 type. It is not AX2 anymore. In the first figure, it is AX2, but with increasing complexity, what we will say, it is the AB2. And here we see only one multiplet, one complex multiplet. So we say it is AB2. It is AB2. Now if we further decrease the value, say 0.3, okay, we will go for 0 value. When it is 0, generally we don't observe 0 for this. Why? Because we have one proton here, two protons here, so that means it is chemically different. This is also chemically, so these two are A and B2 type, they are chemically non-equivalent, so we don't have 0 value, right? Delta nu by J, it never becomes 0 because these two are chemically non-equivalent. So when it is very low, what will happen? The complexity will be very high. The complexity will be very high. Now we will discuss about A to B2 type or A to X2 type. What is A to B2? That means we have two protons on each carbon. We have two protons on each carbon. So these are A type, these are B type. In A to X2 type, they become X. Right. When we have delta nu by J value of around 10, it is a perfect first order. These two protons will give a triplet because they have two alpha protons. Even these two protons will also give a triplet because they have two alpha protons. So based on n plus 1 rule, we can clearly predict the delta values. We can clearly predict the multiplities. And if we want to calculate the J value, just take the difference between any two successive peaks in a triplet. Okay, J value will be the frequency difference between any two peaks. Now it is a perfect A to X2 system. It is a first order spectra. But when we decrease the delta nu by J value to 6, it becomes complex. It becomes complex. So the multiplicity will be complex, which we cannot directly predict based on the. I am just giving these peaks from the book. Okay, follow the Pavia book. Now see, this multiplet is not clear like that. So what we can say, it is becoming second order. So the transition here occurred between delta nu by J value of 10 and 6. 10 and 6. When we take this value as 3, how do we change this? By changing the delta value. How do we do this? By changing the delta value. J value is fixed, coupling constant is fixed. So decrease the delta so that we will decrease delta nu by J value. Okay. Right. When the value is 3, it is even more complex. Here we can see some separation between this multiplet and this multiplet. Here they become even more closure. They become more closure. When we have delta nu by J value of 1.5, then there will be no separation between the individual multiplets. It becomes a single multiplet. It becomes a single multiplet with a complex intensities, with a complex ratio of intensities. When it becomes a single multiplet, we say it is a second order spectra, perfect second order. These are all second order only. Here it is a perfect second order spectra. So it becomes AB2. Can we have a zero value? Can we have a zero value? Yes. Why not? Because two protons on this carbon and two protons on this carbon. If they are chemically equivalent, then what will happen? They will give only one signal. They will give only one signal, and they will not split each other also. Right? They don't split each other also. So we will get a singlet, and it is called A3. It is called A4. A4, because we have 4 protons. It is called A4. Take this correction. It is A to B2. 2 A type protons, 2 B type protons. Now we will consider some examples and we will see their first order, second order spectra. This is beta chlorophenol. When we do this on a 60 megahertz instrument, because of its low resolution, it gives a complex spectrum. It gives a complex multiplet for aromatic protons, as well as it gives a complex multiplet for these two. So this is 7, and we can you see there are two triplets which are closely spaced, 4.2, 3.8. There are two triplets, one triplet, two triplets. This is for aromatic system. Now you see, but clearly there is no separation between these two peaks. Then we call it as A2, B2, because we have two protons on this carbon and two protons on this carbon. We call it as A2, B2 type. But when we do the same, we do collect the NMR of the same compound on a 300 megahertz instrument, it gives a peak like this. This is for aromatic protons. These two are for aromatic protons. We have 5 such aromatic protons. And these two are for, now we can clearly assign 4.2 for oxygen attached carbon and B for chlorine attached. Because oxygen is more electronegative, its delta value will be high, whereas chlorine is having less electronegative value, its delta value will be less. Now we can clearly see a triplet for A type protons, a triplet for B type protons. So in this case, what we can say, it is A2 X2. It is a first order. It is a first order and it is A2 X2 type. But for the phenyl region, it is still second order. For the phenyl region, phenyl group, it is still second order because the multiplets are not clear. But when we collect the NMR data on a 500 megahertz instrument, then we can clearly see a triplet, and a doublet, then followed by two triplets. Of course, delta values will not change. Why we are getting these triplets? It is based on the phenyl groups. Hydrogen, hydrogen, hydrogen. Now, this proton and this proton, they are chemically equivalent. They will give only one signal. This proton and this proton, they are chemically equivalent. They will give one signal, and this is another proton. Now, you look at this. This proton is having only one alpha proton, so it gives a doublet. So this is for HA. Now this proton, it is having two alpha protons, so it gives a triplet. Similar, this proton, it is also having two alpha protons, it also gives a triplet. Generally what we say, the delta values for ortho and para protons will be similar. So if you say this doublet belongs to HA, then this triplet belongs to HC and this triplet belongs to HB. So from this, see, phenyl also second order. Phenyl also first order. This is again A2X2 type because it is a first order in 300 megahertz itself. So generally this second order spectra were encountered in the previous cases in the last 3 decades. before to last 2 decades. Why? During that time, in the initial stages, we have only 60 megahertz instrument. So people used to get second order spectra. But nowadays we have more advanced spectroscopies. So that means 300 megahertz instrument, 400 megahertz instrument, 500 megahertz, 600, 800 megahertz instrument. So when we have high magnetic field instruments, the spectra are very clear and we do observe only first order spectra. Nowadays we are not observing any second order spectra. And one more important point I need to add is, when we increase the magnetic field, here we will have large del J value, whereas here we will have small j value. So that means these triplets become even more clear here. The question, when we expect a first order spectra or a second order spectra, is it possible for us to determine whether a particular compound gives a first order spectra or second order spectra by looking at the compound? Is it possible? Is it possible? Yes. How? If there is a large chemical shift differences. For example, look at this. These two carbons are next to carbonyl, so their chemical shift values will be around 2. Now this methylene group, it is an oxygen, so its chemical shift value will be around 4. This methyl group, it is just an sp3 hybridized carbon, so whose chemical shift may change from 1 to 2. Okay, right? In this case it is giving at 1. It is giving at 1. That means when the chemical shift differences are large, then it gives a first order spectrum. It gives a first order spectrum. But look at the above example. One triplet is at 4.2, another triplet is 3.2. That means the chemical shift differences between these two peaks is small. Then it gives a second order spectra in low magnetic field instrument. But this fellow, the chemical shift difference is very, very large. So we expect a first order spectra in the low magnetic field itself. In the low magnetic field itself. So this gives a quartet because it is having 3 alpha hydrogens, and this gives a singlet because it is chemically equivalent protons. Then this gives a triplet and the values are 4.2, 2.6 and 1.2. Now this spectra was collected on a 60 megahertz instrument. That means if the chemical shift differences are large, then we can easily expect it is a first order spectra. If the chemical shift differences are small, then we expect a second order spectra at low magnetic field strength. But at a high magnetic field strength, the spectrum will have high resolution, so it becomes first order. We will look at one more example. This is, yeah, I'd like to add one more point. See, this is A4 type peak. Because these two are chemically equivalent, they don't split each other, they will give a single signal, and we don't expect any multiplicity, right? They don't split each other. So it is an A4 type. 2 protons here, 2 protons here, it is the A4 type. but this is A2X3. This is A2X3 because we have 2 protons on this carbon, 3 protons on this carbon. It is A2X3 type. A2X3 type. Now look at this fellow. This is A2, B2 or A2, X2 type. Why? We have 2 protons here, 2 protons here. Obviously, the chemical shift differences are very large, right? This is benzylic system. We observe a chemical shift of around 2 to 3. In this case, it is giving a chemical shift value of 3. It is attached to oxygen. We will observe a chemical shift of 3.5 to 4 because it is on a carbonyl group. We expect little more. In this case, it is giving at 4.2. So because there is a large chemical shift differences, we can clearly say it is an A2X2 type. It is a first order spectrum, and it is next to carbonyl group, which generally gives around 2 to 3. In this case, it is giving at 2. Now, when we look at the spectrum, of course, aromatic system will give only one singlet. It is a second order. It is second order at 60 megahertz, but other peaks there, yeah, it gives a triplet. This also gives a triplet. This gives a singlet. 7.2, 4.2, 3.0, 2. This is that means A2X2 is first order at 60 megahertz, but phenyl group is second order at 60 megahertz. If we want first order for phenyl group, we need to go for high resolution NMR. Then we can clearly observe a doublet and 2 triplets. Look at this example. It is attached to oxygen, it is attached to chlorine. Electronegativity differences between oxygen and chlorine are very less. So we can expect these two protons, these protons and these protons, they will have a very less chemical shift differences. Generally, because it is attached to oxygen, we expect greater delta. Because it is attached to chlorine, we expect smaller delta among these two. OH we cannot predict, it varies from 1 to 8. When we take the spectra at 60 megahertz, it is giving a complex spectrum. 60 megahertz, it is giving a complex spectrum. So it is a second order. It is A2 B2 type, 2 protons and 2 protons. So it is A2 B2 type. So this is for A type, this is for B type, this is for alcohol. But when we take it at 300 megahertz instrument, then these two multiplates are separated, but still they are complex. So again it is a second order spectrum. So now also we call it as A2 B2 because these two multiplates are not predicted according to n plus 1 rule. But when we take the same compound on a 500 megahertz instrument, then it gives triplet and triplet and a triplet. Now it is very clear, right? It is A type and it is X type. So this becomes A2 X2 at very high magnetic field. So this is how we compare a second order spectra and first order spectra at low magnetic field and high magnetic field respectively. Now we will look at some more examples. this molecule, it gives this is sorry, chemical shift for carboxylic acid is very high because it is having a withdrawing group. It decreases electron density at this position. So compared to these two positions, we will have more electron density here, we will have less electron density here. Because we have less electron density, we observe high delta here than this. So when we have releasing groups, we observe high delta here because we will have more electron density here. So based on the electron releasing or electron withdrawing groups present on a double bond, we can predict the delta values for these two. I'll repeat. If we have a withdrawing group, what it will do, it will withdraw electrons from the double bond. So it will withdraw electrons from this group. Here we have less electron density compared to this. Because of less electron density, we expect a high delta than this. Sorry, because of less electron density, we expect a high delta. Because of high electron density, we expect a low delta. Right. In this case, it gives a peak at carboxylic acid peak at 12, then a doublet. So this is 7.8, 7.5. These two are for aromatic system. Oh, sorry. This is for aromatic system. These two are for alkenes, 7.8 and 6.5. 6.5. Because electron density is very less here, we expect a high delta. So this is Hb. Electron density is high here, so we expect a less delta. This is Hc. The coupling constant here, it is trans coupling constant, which is around 8 to 15 Hz. This is for aromatic. So we clearly say it is an AX type. So it is a first order spectra. It is AX. When we look at cis stilbene and trans stilbene, we don't get AX or AB. Why? Why? Because we have a symmetry plane here. Plane of symmetry exists here. Here a rotational axis of symmetry exists here. When we have a symmetry element, then what we say, these two protons are chemically equivalent, so they give only one signal. At the same time, they don't split each other. They don't split each other. So here plane of symmetry exists, here axis of symmetry exists. So these two protons are A type. Because we have two, it is A2, again it is A2. We have two such protons. Now look at this example. Because it is a releasing group, we expect electron releasing. So we will have high electron cloud here. So we will get a low delta value here. So these two will get low delta. This will get high delta. Among these two, one is getting high delta, one is getting low delta because it is a electron releasing group. Right. Clearly, when we look at the spectra, this is d protons. So d proton, it is giving a singlet, whereas this is Ha, this is Hb, and this is Hc. Now look at this. Ha, it is having cis coupling and trans coupling. So that is why it's multiplet. It is a doublet because of Hc. Then doublet is again divided by HB. So it is a doublet of doublet. It is a doublet of doublet. Because it is having cis coupling and trans coupling, generally the cis coupling will be 6.3 hedges, trans coupling will be 14 hedges here. So we observe a large separation among the peaks. But here you see it is again a doublet of doublet, which is for B. But see what is having B? B is having one trans coupling, one geminal coupling. Geminal coupling value is very less, right? Geminal coupling value is 1.5 hedges. That is why we are having very less difference between this doublet and this doublet. But these two doublets are well separated because it is also having trans coupling. Okay, but now look at this. This is again a doublet of doublet. See, but see, the doublets are not well separated. They are compared to other, they are less separated. Why? Because it is having geminal coupling. Geminal coupling is very less. Geminal coupling is very less. Then it is having cis coupling between A and C. Cis coupling is also very less. So that is why these multiplets, they are closely spaced, whereas these multiplets are broadly spaced. So from this also we can clearly say whether which protons are coupling. So based on the multiplet arrangement, we can clearly say which protons are coupling here. Because wide separation we expect large coupling constant, because of small separation we expect small coupling constant.